have enough, there's enough weather stations out there to describe weather on the importance scales. Is there any proof of this? No, it's just crap. But we believe it. Okay. What else do we believe in? Weather balloons. That's how we observe weather. Radar stations. Satellite pictures. Maybe the occasional fancy thing like the sounders or LiDAR stations or special balloons or whatever. Right? We have some idea of how mid-latitude meteorology gets it done. Like countries that have a bunch of money and who know what they consider important in their part of the world. What kind of observing systems do we have in the tropics? I'll be talking over the course of, it takes us about 4 or 5 lectures to get through all the observing and all the related topics associated with it. We're going to talk about how we observe and why we care about sea surface temperature. If you're not familiar with that abbreviation, SST, sea surface temperature. You'll be seeing that forever in this discipline. I didn't make that up. We'll talk about the business of how we observe the atmosphere and how we analyze the atmosphere in the tropics. You know, if you're in a part of the world where there aren't big differences in the pressure, we talked about the fact that like pressure gradients were small in the tropics. Well, then probably drawing a map of pressure with isobars on it, the way you did in other classes, probably isn't going to be real helpful in the tropics. We're going to need other ways to make maps that tell us what's going on in the tropics. Doing things like streamlines and isogons. If you don't know those words yet, don't worry, you're going to be learning all about it. Or working with the divergent and rotational flow, so-called stream function and velocity potential. Okay. This is something we'll be learning about quite a bit. You need other ways to describe the atmosphere in the tropics. And we're also going to talk about precipitation. Man, it's wet in the tropics. And most of the tropics is ocean. And what is an ocean is developing countries, by and large. Okay? Not places that are going to have some great radar systems set up for observing. How are we going to do this? How are we going to observe the precipitation going on in the tropics? So this is what we're doing for the next several lectures. Actually, most of the way to the next test, actually. That's pretty close. Also talking about some main features of the atmosphere. But okay. How are we doing on time? I've got an alarm set to go off in 11 o'clock. 20 minutes out, we're in great shape. Okay. Students often haven't thought about it this way yet, but the ocean is this incredible black body, if you will, that absorbs just incredible amounts of solar radiation. The oceans are sitting there under the sun 365 days a year. Tropical oceans, every one of those days of the year, the sun is pretty much directly overhead. And the sunlight is penetrating into the ocean. Now, you may not have ever thought about it this way, but every little bit of heat that goes into the ocean has to eventually come out of it. Okay? No heat goes through the ocean and comes out the other side of the earth. Right? If it goes into the ocean and gets absorbed by the ocean someplace along the way, sooner or later that heat comes back out of the ocean. Maybe not right there. Maybe ocean currents transport it someplace else and then it comes out of the ocean. But sooner or later, all that heat has to come back out of the ocean. And again, you may never have thought about this, but the ocean is actually really, really dark. The ocean actually does not reflect very much light from the sun. You probably know the vocabulary word albedo. Albedo has to do with how reflective a surface is. These walls have a very high albedo. Most of the light that hits them is reflected. This chair has a relatively low albedo. Most of the light that's hitting it is being absorbed. Only a little bit of the light is being sent out. Right? Oceans have a very low albedo. When you look at a visible satellite picture, they're pretty much black. That's because most of the sun's light that hits them is being absorbed, not being reflected. In contrast, of course, the albedo of these clouds is very high, right? It's reflecting light, that's why they look white. So here are the oceans, sitting under, especially the tropical oceans, sitting under the sun 365 days a year, high sun angles, so we got lots of sunlight penetrating into the ocean, and they're basically black. They are absorbing almost all that heat. So the ocean becomes this incredible reservoir of heat. By the way, that's part of the reason why hurricanes happen, right? Hurricanes are an effective way of getting heat out of the ocean back into the atmosphere. You know, blowing a wind at 165 miles an hour across the ocean tends to cause a lot of mixing, a lot of evaporation, a lot of sensible and latent heat fluxes. If you don't know those terms, don't worry. You will now. So there's all of this heat being stored in the ocean, and it's all going to come back out. That makes the temperature of the water extremely important. Right? Because that's measure of how much heat is in there. Now, the atmosphere only interacts with the ocean at the surface. The atmosphere has no way of knowing what's going on deep in the ocean. So, while it's true that the deep ocean is what's important, right? That's when all that heat's being stored. Well, not say deep ocean, not the surface. In practice, the surface is the only place that's interacting with the atmosphere directly. So we need to keep track of the sea surface temperatures. And over the tropical oceans, sea surface temperatures is easily the most important variable or parameter for describing what the ocean is doing. Sea surface temperature is the strongest controller of what we call the sensible heat flux and the latent heat flux. Let's just pen here real quick here. So I want to make sure we're clear about these terms. Sensible heat flux and latent heat flux. I'm not going to write the word flux just yet. Everybody here's a survivor of intro. We have all learned about conduction. Conduction is about when two surfaces with different temperatures are touching each other, like your relatively cool hand touching a relatively hot handle of a pot on the stove. There is conduction because the two surfaces are in different temperatures and heat moves from one to the other. Scientists can't leave that alone. That's called sensible heat. Okay? I don't know a good definition for sensible heat. Okay? It's about moving heat. Moving heat through objects that are different temperatures. When relatively cool air blows across warm oceans, there is a sensible heat exchange between the ocean and the atmosphere. Heat comes out of the ocean and moves into the atmosphere. The rate at which that happens is the sensible heat flux. Sensible heat flux. Survivors of the dynamic sequence know all about fluxes. Yeah. Flux is the rate at which something moves. When the water is warm and the air moving over it is cold, there's a huge sensible heat flux. As heat moves out of the ocean and into the atmosphere. When the water and the air are the same temperature, there is a low sensible heat flux. See how the water temperature is going to be important? As we are having warmer and warmer waters, we'll have a faster sensible heat flux out of the ocean into the atmosphere. Latent heat is about evaporation and condensation of water. We all know that evaporation is a cooling process. That's why sweat works, right? You evaporate sweat off your skin, you cool down. We all know condensation is a warming process. Condensing water in a vapor into liquid water droplets in a cloud releases latent heat. This word latent is always a hard one to use in a sentence. One of these creepy old words that still sneak around in science. Probably the easiest way to think about the word latent is to think of the word hidden. Like, Jason has a latent desire to kill his roommate. Okay, it's hidden. He doesn't go around talking about it, it's just his latent desire. Right? I hope no one's roommate's not here. Okay. Alright. So this is latent heat. Right? The air didn't change temperature because it had evaporation, but yet it has absorbed heat out of the ocean. And the rate at which this happens is the latent heat flux. Or latent heat flux. So latent heat flux is all about evaporation at the ocean surface. Evaporation cools the ocean. Later that water vapor will condense someplace in the atmosphere, and you will have heating in the atmosphere. You have moved heat from the ocean to the atmosphere. That's how hurricanes work, right? 165 mile an hour wind blowing across the ocean, you get a lot of evaporation. That cools the ocean. You take that heat in the form of water vapor someplace else, and you have condensation, you get the latent heat back. All right. So we need to know about the water's temperature. By the way, the rate of latent heat flux, warm water evaporates more easily than cold water. So that's part of the reason why hurricanes only happen over warm water, is because they need that warm water to have enough fast enough evaporation rate, enough latent heat flux to keep the hurricane going. All right, so we're all in agreement here. You've got to have a strong knowledge of the sea surface temperatures if you're going to be describing tropical meteorology. Sea surface temperature can be measured by buoys. That's a Creighton graduate, by the way, up there on top of the storm. He's an environmental science graduate who now he works on buoys. He sent this picture of himself resting on a buoy. That wasn't a ship, had to sail away. Anyway, you can have different kinds of